Yes. Thank you, Elaine, and thank you everyone for being here. So I'm from the Scientific Computing and Imaging Institute at the University of Utah, and I'll be talking about our collaborative work on neural network models for neighborhood effects research. So the first part of my talk, I'll go over how we construct built environment features using Google Street View images, and then examining the relationships between these features and demographic characteristics of residents and health outcomes. And in the second part, I'm going to talk about some models we built for alternative forms of supervision, trying to alleviate the burden of image labeling. So Google Street View was launched in the United States in 2007 and provides high spatial resolution, eye-level images of neighborhoods, businesses, homes, streets. We started this project in late 2016, collected about over 400,000 images across 3 cities in the United States, Chicago, Salt Lake City, and Charleston, representing different population densities and different visual characteristics. Images were collected from all road intersections in these cities and random sample of street segments. Then we labeled 3 built environment features. The first one is whether a crosswalk is present in the image. The second one is the type of building we see. So this is either single-family detached housing or other, meaning it could be multi-family housing or commercial building. The third one is the level of street greenness, whether at least 30% of the image consisted of trees and landscaping. All 3 of these are binary type of features. So we then used a deep convolutional network, the VGG19 model to be specific, which is commonly used in transfer learning. So we take advantage of this model, which has been trained on a much larger data set, the ImageNet, for image classification. And then we labeled 16,000 of those 400 and so thousand images we had collected for the 3 built environment features. And then we do the traditional machine learning testing paradigm where we split, in this case, 80% for training the model and 20% for testing. So we fine-tune the VGG model on using that training set. Then we evaluate on the testing set, and we obtained accuracies in the mid-80s for 2 of the indicators, the single-family housing and whether the streets were green or not, and then 93% for the presence of a crosswalk. So once we validated the model, let me show you a couple of images what this looks like. So in this case, you see an image which has more than 30% greenery and has a crosswalk, and the buildings here are not single-family housing. Another image. So this one's perhaps interesting. So it is predicted as green 30, for instance, has at least 30% green, even though it's a winter scene and the trees are not green. Of course, machine learning models are able to deal with this as long as you have similar images in your training set, right? So that is not a problem. So once we validated then on the test set our accuracies, we can then deploy this on a larger scale on all those 400,000 images we had collected. So we did that, and so then we analyzed the results, for instance, at the zip code level for the different cities. This is showing the distribution of the 3 built environment features for Salt Lake City, showing the different tertiles from light green, the lowest tertile, to red, the highest tertile. So Salt Lake City is a desert type of environment. So if you look at the rightmost zip code graph there, as you go east in Salt Lake City, you go close to the mountains, and the streets become a lot greener, and that is what we see. So maybe that's a second level of reality check that the model is doing what it should be doing. Then we looked at the correlation of these built environment features we extract with the computer vision model, and adult obesity and diabetes rates at the zip code level. And we take the lowest tertile as a baseline and look at the prevalence ratio, and we see that at the highest tertiles for all the 3 indicators, we see lower disease rates. So green streets, presence of crosswalks, and presence of not single-family housing, so commercial buildings, provide some protection against obesity and diabetes. So then we started the second part of our study, and we started collecting a much larger data set in this case using the census, 2017 census to identify street intersection coordinates, and then using Google Street View's API to get those images, around 30 million images, added some more indicators. But then this brings us to a challenge that when we're looking across the US, having labeled images from free cities is not sufficient because there's a lot of variation in architecture and landscaping across the US. So the model would need a much larger annotated training set to generalize well. And of course, that's costly and hard to do. So can we get away from that? Additionally, the designed features, as we call them, the built environment features, are hand designed, may not be able to capture all the relevant variations in the data. So we proposed then a direct regression model that tries to get away from this problem of labeling. So still using a deep convolutional neural network, but in this case now, instead of single images, we take images, a set of images from a census tract, and we build a network which is permutation invariant. So we have an aggregator in there, such as a simple mean of features. And then we directly try to predict the disease rate. So this gives us now freely available signal for supervision, disease prevalence rates at the census tract level available from the CDC. As a baseline to see how this would compare to if we had done the regression from the built environment features we predict, we compared to this model where we trained the model for extracting the built environment features as I already described. Then we freeze that part of the model and then train a simple linear regression using those as input features for the disease prevalence rates. Okay, so we have disease prevalence rates for about 19,700 tracts corresponding to 7 million images. So we do 5-fold cross-validation on this data set using coefficient of determination, so the goodness of fit, to compare them. And what we see is that this direct regression model, which goes from the images to the disease prevalence rate, so the black box model, if you will, does significantly better than the baseline regression model. So perhaps that's not surprising because that's the whole promise of deep learning, where you don't try to design features by yourself, but let the model learn. And if you have sufficient data, that's supposed to work well. So this just another confirmation of that. However, of course, the model is a black box there, so we no longer have the built environment features to correlate with the disease rates. And we can then try to combine both those approaches into a hybrid model where we simultaneously predict at the single image level, these built environment features, but at the same time use the same model to do the census tract level disease prevalence rates. So it looks something like this, but that's probably not going to go too much into detail here, other than to say that the model is trained end-to-end here, but has two types of, so multitask type of loss, where one loss is for the disease prevalence rate at the census tract level, and another one is for at the image level, whether the built environment features are present or not. And of course, the training set for one is much bigger than the other. So when we added the two models together, not only the performance goes up a little bit, which is nice, so the hybrid approach does outperform the direct approach, so the built environment characteristics using them in the model provided some benefit, but also now you can predict both things at once, and if we're interested, we can look at the predictions of the built environment characteristics and see how they still correlate with our disease rates. So to conclude here, we are now into a much bigger data set collection, 170 million images. And we are going to run the computer vision indicator models on this in the coming months. We are also interested in explainable machine learning models. So for instance, in the context of a different project on radiology project where we try to predict certain diseases from chest x-rays, we're looking at how we can build explainable models where the model not only makes a prediction, but also tries to provide a visual explanation of what constituted that decision. And if the image changes like this in this certain way, then I wouldn't have called it this disease. So we're interested in such models, and eventually we want to build them for this project as well. So I'd like to acknowledge the National Institutes of Health, which funded this project, and our collaborator at the University of Maryland, Professor Nguyen, and the graduate students at Utah who did this work. Thank you.
I have one question on the correlation in green versus not, and the links to obesity and diabetes. Wouldn't is your model better than, say, using zip code data or a more detailed, already existing indexes of poverty and so on? Did you compare them?
So unfortunately, I'm the computer vision guy in the group, and I'm not very familiar with what's the state of the art outside, so I couldn't answer.
So you could, not to minimize the work is cool, but you could bypass the image processing and then just try that, and then see how much the image adds to that.
So to use what?
In general, what has been found, that somebody mentioned the food trends, Google food trends, it was shown that it works better when you use it integrated with the CDC data.
Mm-hmm.
In this case, it will be an interesting thing to show that if you just use traditional sources, which is all the stuff that we already have on zip code and income levels and all that other stuff, and housing, median house price, all that. If you use only that and correlate with diabetes and obesity, and then you add your stuff, and you show that it's better, then you have something that's very simple.
I agree. That would be very interesting. Yeah, something to look. Yes. Thank you.
I think one of the broader goals of the project was to create a sense of the whole environment, to be able to track that over time to see how it changes too. Is that correct?
Yes, right. To track it over time. I mean, I guess one of the nice things about the model here is once you've trained, you can deploy it at scale. So certain things might perhaps be easier to do, like track things over time. But I do agree also that you should look into existing sources of data and if this adds anything to it or not. Yes, and there's a second part of this project, a different part of this project, which I'm not involved in, where actually Professor Nguyen is looking at Twitter data to kind of predict the same things as well.